of the notes. Tomorrow is our first lab, so we kind of take a little bit of a break because we really have like 3.5 days of lecture. So this is day 2 of it. Couple changes to the notes, but you'll see those as we kind of go through this. It's just certain formulas you need, certain formulas you don't. You'll need your charts, your reduction potential chart. You're going to need a calculator today. And if you got your formula sheet handy, maybe get that out too so you can kind of refer to some of the formulas that they provide for you for that. Okay, so the formula sheet I gave you kind of early in the year. So first thing what we're going to do is we're going to practice what we learned yesterday. All right, except this is kind of like a slightly new condition here. There's something about this problem that's different that we did not mention yesterday, but this would be the good time to bring it up. So we're going to practice drawing a cell that's made up of silver and iron 2 and iron 3 ions. So we're going to draw the cell itself and then just write out this line notation for it. So with this particular one, we got 2 reactions taking place. So we have silver ions being reduced into silver metal. And then we have iron 3 being reduced to iron 2. So I need your help. You need to look up these 2 items on your reduction charts and tell me what my E values are for each one of these. So I need to know what those are. So find them for me, please. So we need to know which one's oxidized, which one's reduced. Okay, Annie, what do you got?
For the AG it's 0.80 and for the FE it's 0.77.
Okay. So knowing that, which one's oxidized, which one's reduced? Which one's reduced? AG is reduced. Fe is going to be oxidized. So in terms of me drawing out my cell, which one's going to go to the anode, which one's going to go to the cathode? What's that? The AG, what's going to happen? Where's this going to be, anode or cathode? Cathode. So we know this is going to take place at the cathode, and this is going to take place at the anode with them. All right? Okay, so go ahead and draw your cell. So you have your 2 beakers connected. You have an electrode in each one of these with a voltmeter coming off of that and a wire connected to it. And then you have your salt bridge, which is connected to it as well. Draw your solutions for this. Now, creature habit, as I said before, if I'm drawing these cells from scratch, I usually just do anode on the left, cathode on the right. But again, you can have situations where they give you cathode on the right or on the left and anode on the right, okay? It doesn't always have to be that way. It's just the way I do it when I draw them out. Okay, let's come back to this one. Let's focus on this one first. Let's focus on the cathode. So the cathode, we have the electrode, which is silver, right? Because it's silver metal. What's the solution going to be? Silver ions, Ag+. What's the concentration going to be if it's standard conditions? 1 molar. Go ahead and make that 1 molar as well. Okay, now the other side. We got a problem here. We have ions and we have ions. So if we have ions and ions, what's the electrode have to be? We talked about this yesterday. It was one of the ones that I said where it's not, if it's not a solid metal, there's something you have to use. And we were talking about with hydrogen yesterday. An inert metal. And what was the example that we were using yesterday? Anybody remember what metal that was? It's expensive. Starts with a P. Platinum. So, can you go ahead and write PT on that electrode? We know that it's platinum. Okay, well, in this solution, what are we going to write for ions? Well, we actually have 2 different types of ions here. So we're going to write Fe2+ and Fe3+. Both ions are in there, and the oxidation is technically taking place within the liquid itself. Which way are the electrons going to flow? From what side to what side? Anode to cathode. What was the phrase that we used for that? Fat cats. Good. Okay. So we have electrons going from anode to cathode. Now, let's go ahead and figure out our cell with this. Okay, so which one of these two am I going to flip? The top one or the bottom one? The bottom one. So I got to change the sign. So if I change the sign, now make this negative, what's my overall cell output for this cell? 0.03. So you are going to write 0.03 volts within your voltmeter. Like so. Okay, now the salt bridge. Remember there was a nice little kind of phrase or whatever I gave you yesterday, or a nice little memory device to help you remember that? The salt bridge is made up of potassium ions and nitrate ions. Which ones are going where? Remember from yesterday? The cations go to the cathode and the anions go to the anode. So that means that you want to say K plus coming out this side and NO3 minus coming out that side. And technically speaking, your liquid levels should be, the tube should be going into the liquid levels. They don't just travel through air, just fall from, use gravity or anything like that. It's within the solution itself that it actually takes place. Okay? All right. Are there any questions with that part of this? We got to do the line notation next. No questions? Okay. Line notation. So, remember we said that first it's the anode. So what is the anode that we used in this reaction? Platinum. So you're going to say PT. And let's, I know we kind of get away from doing states of matter. Let's do states of matter with this just so we're indicating certain things with this. Okay, what's the next thing I'm going to write? It's the anode solution. What's the anode solution going to be? Fe2 plus, aqueous, comma, Fe3 plus, aqueous. Then what do I write next? Who remembers from yesterday? Double line. What does that double line kind of symbolize? Like the salt bridge. Okay, what's next? Cathode solution. So what's the cathode solution? Ag plus, aqueous, single line, Ag solid. Like that. Very good. Any questions with that? So hopefully that works. Okay, this is a unique situation because we haven't done one where it was just ion to ion. It was everything we did yesterday was like ion to metal, metal to ion, so on and so forth with that. So we wanted to make sure that you guys are kind of clear how you do one, because there's many examples that would kind of fit that criteria for this. All right. So yesterday we talked about the connection between G and E. Yes?
For the line notation, does it matter like which of these first?
Good question. No, it does not matter. Nobody's actually asked me that before, but no, it doesn't matter. It's just a matter of, do you make sure that you have it in the right position where all the lines are, okay? So order though, it does not matter. It'd be kind of like doing a balanced equation where you're writing equations, you're like, do I write this one first, this one? Doesn't matter, just make sure you have them both there. Okay, so we talked about yesterday the connection between G and E. We were saying that if E is a good battery, that means it gives off energy. It's spontaneous, so that means G has to be negative. So they're opposites of each other. Today we're going to learn how to calculate that. You guys have your calculators. We're going to be storing something into the calculator, so get those out if you haven't already. So the formula that we're using with this is G is equal to negative NFE. G, delta G is equal to negative NF E naught. So what does it represent? N is the number of moles of electrons that would be transferred in a balanced redox equation. So when you figured out, let's say it was like you had 2 for one and then 3 for another, you had to multiply, find the common denominator between the two, so 6 electrons would transfer. That's what N represents. F is Faraday's constant. We're going to store this in our calculator. So in your calculator, can you type in 96485, that store button, which is like either bottom left, bottom right, somewhere out there. Store that as capital letter F in your calculator. And what it is 96,485 coulombs charge per mole of electrons that passes through. So every mole of electrons that would pass through a wire, it's that many units of charge. And then E we know is just basically its cell output that we have been calculating using our charts. So it simply implies this, or it follows that if you have a negative E, it's a non-spontaneous situation, because if E is negative, G is positive. If E is positive, it is spontaneous, and it would be a good battery because we're looking to supply energy, not require energy. That's the difference between these two. This one supplies it, that one requires it. Other things to mention up on your charts, taking a look at your charts. We noted yesterday where things are likely to reduce, where things are likely to oxidize. The more likely something, it says the stronger the oxidizers, the weaker the reducer, so on and so forth. So if you're looking at your E values, the higher up on the list it is, the more likely it is to reduce. So that means it has excellent oxidizing ability. The lower it is on the list, the more likely it's going to be oxidized. So that means it has really good reducing ability. So that's, just make sure you do understand that on your chart with this. So what we're going to do is we're going to practice a question using this formula, using your charts to solve for all this stuff that we actually have. So we got two equations here, or one equation but two half reactions. Let's write them out. Cu2 plus yielding Cu metal. So copper ions yielding copper metal. And then we have iron metal yielding iron ions. So if I'm balancing half reactions, I got to do electrons. How many electrons on the top one and what side? 2 to the left. Bottom one, how many? What side? 2 to the right. They balance each other out. It's 2 and 2. We don't have to do anything in terms of multiplying by coefficients. So what does that tell me N is? N is equal to 2, because 2 moles of electrons will transfer. So we're going to say N is 2 moles of electrons. All right. Knowing this, we got to look these values up. What is the E value for the reduction of copper? Copper 2 to copper metal. There's 2 different coppers on there. You got to look at the appropriate one on your list. So look at your charts. Find copper 2 to copper naught. What's its value? What do we get? 0.34? Okay. Now find iron 2 going to iron metal. Iron 2 going to iron metal. What is its reduction?
Negative 0.44.
So it's negative 0.44. So if we're doing the opposite, we're going to say 0.44. Because it's being oxidized. Okay, so what's the overall cell output going to be? 0.78, right? 0.78 volts. Okay. So, having that information, we can go ahead and solve for what delta G is going to be. So we will say this. 2 moles of electrons times delta G is equal to negative 2 moles of electrons times, you can say F, but I'm going to write it out so you can see what cancels. And we're going to multiply this by 0.78. It's volts. Does anybody remember what I told you the ratio, what a volt actually equals? Joule per coulomb, yes. Okay, so if these are all my units, and we cancel everything out, what are we left with in the end? Joules. And that should make sense because we're talking energy here, and energy is joules. So what, go ahead and calculate it. Figure it out. What is my answer for delta G in this particular one? In joules. Now, let's talk sig figs for a second too. This is a counting number, so you ignore. This is a constant, so you ignore. So we're going to focus on that number right there to give me my final answer for sig figs. So how many sig figs do I need? 2. So what would my final answer be? You can give it to me in joules or kilojoules. Delta G is typically expressed in kilojoules, though. So if it's kilojoules, how many is it?
150 kilojoules.
150 kilojoules with or without a decimal?
No decimal.
No decimal, that's right. So 150 kilojoules would be the answer. You could still say 150,000 joules. Still the same thing, unless if they say express the answer in kilojoules. Yeah.
Why is it positive and not
Oh, no, that's my fault. It should be negative. I forgot to say, you may have even said negative, I just didn't write it down. I don't even know, but it should be negative. Thank you for asking immediately for that. So any questions with that? How to do this? So again, this is just showing you the connection, the mathematical connection between G and E. If they have you calculate between one versus another back and forth, you now know how to do that with this. Okay. So moving on, there is an equation. So everything we've talked about so far have been standard conditions, meaning that all of these cells are 1 molar concentration. But you're going to come across situations where the cells are not at standard conditions, non-standard conditions, and that's what they use this equation to refer to as the Nernst equation. So simply put, it's just saying that this is the standard potential in normal conditions, but this is what it would be in non-standard conditions when we apply this formula to it. So N represents moles of electrons from what we had before. Q is going to be products over reactants, and it's the concentration. And more times than not, it's going to be like your anode concentration divided by your cathode concentration with this. Not all the time, but most of the time that will be this case. Okay, so take a look at this. Now remember yesterday I showed you that picture where it was zoomed in saying like, okay, this is what's happening at a micro scale level. So I have 0.1 molar and I have 1 molar. And these two concentrations want to be equal to each other. The only way that's going to work is if this concentration goes up and this concentration goes down to reach equilibrium between the two. Which way would the electrons have to flow if I want this concentration to go up and this concentration to go down? And you can look, if you want to look at your slide from yesterday, you can, that one where it's zoomed in, but I want to see if you can figure that out. Which way will it go? What do you think? 0.1 to 1. Okay, why would that be the case?
Because the atoms are like splitting off in that ion, like increase the concentration, and then the other one, the ion become atoms.
Yes, exactly. So in this one, when the electrons leave, the atoms become ions, as you said, and then when the electrons are now attached here, it's pulling ions from solution and attaching them on here. What's going to happen to this electrode over time? It's going to get heavier or more massive. What's going to happen to this one? It's going to start to like erode away, like this. Okay? So the electrons, it's important to know what side the electrons are going to be traveling for, because we need to know what side's the anode, what side's the cathode. So would this be the anode or the cathode then? This is the anode, because we know we go from the anode to the cathode. All right? So determine which side goes oxidation. What happens at the anode? Oxidation or reduction? Oxidation. So this is my oxidation side. This is my reduction side for the actual reaction. It's important to know that because when we have those, we can write our two reactions out. So we have, this is my reduction. Zn ions going to Zn metal, 1 molar concentration. This is my oxidation. So if I cancel out like terms, like so, the only thing I have left over is this. Higher concentration going to lower concentration in the balance equation. This is my products. This is my reactants. So that will help me determine what Q actually is, because Q is the concentration of products over reactants. So we would then plug that into the equation. And there's a lot of stuff written here, but let's just kind of take it little by little. So in this particular one, 2 electrons transfer, because we go from Zn2 plus to Zn naught. So we know that N is equal to 2. Since it is talking about zinc and zinc, if the concentrations at standard conditions would be exactly 0, because if it's the same metal, same solutions, there's going to be no passing of electrons. Not one side's not going to favor another with this. We just determined Q a second ago, which is 0.1 over 1. So now it's as simply as putting the information in to solve for what E actually is. So Essentially what happens is this. Your cell goes from a 0 volts to 0.03. So it increases in voltage in that situation. That will only happen if Q is less than 1. If Q is greater than 1, the exact opposite applies. It's going to have a negative cell voltage to it, so it's losing more. It's going in the negative direction with that. So connections with this, and what you would be expected to know for AP would be this. I think you guys have this slide, right? I kind of changed it around a little bit. Calculations using the Nernst equation will not be on there. The formula is not given to you, so you don't have to worry about doing the calculations with it, but you need to understand how it's going to change based on the reactants or the products changing concentration, okay, whichever one's doing what with that. So if the reactants are greater than the products, cell potential increases, and vice versa in those scenarios. All right, so just always know what's happening concentration-wise, which way it's going to favor with electrons, what size oxidation, what size reduction, and that's where this question kind of comes into play with this. This is a normal question that they would ask. So if I give you this cell right here, 2 electrodes of iron, 2 different concentrations of iron, which way will the electrons flow in this particular question? They're going to go from the lesser concentration to the greater concentration every single time. So it's a lower concentration to the higher concentration. So when they do that, it's then going to reach equilibrium where this will go up and then that will go down. So always remember that if it's different concentrations, the same electrode, it always goes from the lower to the higher concentration on the cells. All right. This slide, I think the next slides, the last couple slides we have left, are some changes on there. So when you are at equilibrium, we're no longer talking about Q. Q now has become K. So we're going to be focusing on K. So when you have a situation where you're at equilibrium, first thing to tell is this, is the battery is what you refer to as dead. Like your cell phones, when they die, that just means they've reached equilibrium. So cell potential no longer is providing energy to power the cell phone, so the cell potential is at 0 volts. As I said, Q becomes K now. And there's 2 formulas that we're going to actually use that show the connection between E and K that AP would expect you guys to look at. First one. Last chapter, we learned that delta G is equal to rat link. So negative RT natural log of K. This helped us determine the connection mathematically between G and K. This chapter we're using G and the connection that it has with E. So if AP asks you a question where they're asking you to see what's the mathematical connection between E and K, well, since this equals delta G and this equals delta G, that means they equal each other. So what that tells us then is, skipping the negatives, RT natural log of K is equal to NFE. They're equal to each other. I told you to get out your formula sheets if you had them. If you look on the back and see your delta G's, that's what they actually give you for those. So if they ask you to solve for a question where they give you E and they ask you to solve for K, they would expect you to do it this way, or vice versa, one or the other with that. We're going to practice that with a couple ones. So I gave you one, I think this has like a lot of stuff written there. Let's put an X through it. We're going to solve for this a different way. So put an X through that math that they actually show you on this particular one. We're going to go ahead and solve for this. Now, if we are using this formula right with this, first thing I'm going to need to know is, what is my N? Would you be able to tell me what N is without writing out the half equations and balancing everything? Do you know what N is? What is it?
2.
It's 2. What's obvious evidence of that? We know this is going from 2 to 0 and this is going from 0 to 2. So you know 2 electrons. And quite honestly, guys, it's the common denominator between the two is what determines that. So N is 2. All right, and we're trying to find K. We're calculating K. So we're going to say RT, natural log of K, is equal to NFE. I got to isolate K. So I'm going to divide both sides by RT. So now I have the natural log of K is equal to that. How do I get rid of my natural log again? E to the X. So we do E to the X on both sides. So essentially this entire thing right here. So we would say 2 times F in your calculator times 1.1 volts. What's my R value again? What is it? 8.31 times, it's at 25C, so what I need at temperature, I need it in Kelvin. That would be 298. Okay. Once you get that answer, I need this then express it exponentially with your e to the x. And that will tell us K. And remember what we know about K is that if K is greater than 1, it's forward favored. If K is less than 1, it's backwards favored. But what do I get K? It should be a pretty big number. What do we get? You have an answer?
Yeah.
What do you got?
1.68 times 10 to the 37.
1.68 E37?
Yeah.
1.68 E37, is that what others are getting as well? So what does that tell me in terms of forward versus backward favored? It's so ridiculously favored in the forward direction with that. It's saying that it's like, you know, it's 99.99999, like 37 nines essentially. It tells you how much percentage-wise it's being forward and favored in one direction versus another with that. Okay, we're just gonna practice one more of these. And I wanna see if you guys can do this one. So last slide of the day is this. Giving you this information right here. This is balance the redox reaction. Calculate E and calculate K at 25C. So give it a shot, see if you can do this on your own. Don't forget too, we got test corrections today after the first bell. You were doing those. If you're not doing test corrections today and you have not done test corrections, that means you will be correcting 3 out of the last 4 tests. And I'll talk to you about when you're looking at the tests. Were you here on the test day? You just missed sense time, right? I think it was hard. Really, when you're balancing the redox reaction, all you'd have to do is just put coefficients up here where they would apply. If you kind of think about it, since they give you the reaction with that. I'm already telling you, if you look at this, you know which one of these two we have to flip based on looking at this up here. So which one of these two is different? Top one or bottom one? This one, right? This one would have to be flipped. So that should say what? Plus 0.5. So that means my cell output is 0.67 volts. Yes?
Do you not have to multiply the one by 2?
We will have to, but we will never touch E when it comes to multiplying. Because remember what we said? A volt is a joule per coulomb. It's a ratio. So that would just mean I'm doing this, Braden, times 2 times 2. If I do top and bottom times 2, it simplifies to the same thing. So do not touch that regarding that. But we would be multiplying this by 2. So that means that my N equals 2. This would need a 2 up here. This would need a 2 up there. So it's a balanced redox reaction. We already calculated so we've done this. We've done this. Now we just need to solve for K. So K, as we said from before, the natural log of K is equal to NFE over RT. So N is 2 times F times 0.67 volts divided by 8.31, and it's at standard condition, so it's going to be 298. You have to take the e to the x for that. Got an answer? 1.72 times 10 to the 4.72? 4.72 times 10 to the what? 22nd? So E 22nd? Again, something that's so heavily favored in the forward direction with that. Okay? All these cells with this, you're gonna have E's that are gonna be, or K's that are gonna be heavily favored in the forward direction until we start talking about something that needs a battery. Once it needs a battery, now it's gonna be going in the opposite direction with that instead. So it would be going opposite of that. You would need to have like a battery to operate a cell then at that situation. I think it's the last slide, right? Yeah. Okay. So you're gonna finish problem set 1 today, move on to problem set 2. We're giving you the worksheet tomorrow on the day of the lab. Lab number 1's tomorrow. Who's doing test corrections today? 1? Just 1 person? 2?
Yeah.
You're gonna use your last one?
I think so.
Okay. All right. Now it's really gonna be roll the dice. Gambling. Okay, so that is it.